Hi, welcome to Chapter 15, Chemical Equilibrium Overview Part 3, which is our last video for this chapter, where we're going to talk about applications of equilibrium constants and Chatellier's principle. How do you know if a mixture is at equilibrium? And if it's not at equilibrium, how do you know which way the reaction is actually going to go so it can get to equilibrium? Well, to answer these questions, we have to calculate something called a reaction quotient, or Q. Q actually looks just like K. The same way we calculate K, we're going to calculate Q. Except for Q, we are not using equilibrium concentrations. We are using the concentration that we currently have. It could be the initial concentrations or just the concentration that the reaction is currently at. So to calculate Q, you're going to substitute your concentrations or pressures of the reactants at any given time during a reaction. The purpose of Q is to help determine which way the reaction will go. And you have to ask yourself, is it creating more reactants or products? And that'll help you determine which way the reaction will go. So in nature, you want Q to equal K. Okay? But that's not always the case. So let's take a fake reaction here, so we can kind of understand what this Q is. And if I wanted to write the equilibrium K for this, I take my products raised to whatever coefficients I have here. Everything's 1 here, so keeping it simple. And then I take my reactants raised to whatever coefficients are there. And these concentrations here are at equilibrium. Q looks the same, except your concentrations, sometimes you'll see a little I here. That I means initial. That's the concentration that you're starting with, or it could be the concentration at any point in time during the reaction. They do not have to be at equilibrium, okay? But if Q equals K, that means it is at equilibrium. So if Q equals K, then you are at equilibrium. Well, what happens if Q is less than K? So at this moment in time, your Q value is actually less than your equilibrium value. If Q is less than your equilibrium value, which term is too small, the top or the bottom? So you want Q to equal K. But if Q is less, that means the top is too small. And the top is your products. That means you need to make more products. And in order to make more products, your reaction will move forward. Now, what happens when Q is greater than K? That means you have too much products. Your top is too large. So if that is the case, you need to make more reactants. So you need more reactants. So the reverse reaction will proceed. And it's just going to proceed that way until you get to Q equals K. So this is if you're starting with random concentrations of all of these, okay, and then you need to know which way the reaction is going to go. It's kind of handy, actually. So again, if Q equals K, they are equal. You're at equilibrium. So the reaction is not going to shift one way or the other. You are at equilibrium. If Q is greater than K, then you have too much product. And how do you get rid of product? You move away from it. So you're going to shift to the left to make more reactants. See here, Q is too large, so you need to shift towards the reactants. If Q is too small, that means that you don't have enough products or you have too much reactants. So you're going to actually shift to the right so that you could get your K and your Q to be equal. So here's just like a summary comparison of K and Q. So if Q is less than K, there are too much reactants. There's too much reactants. You need to increase the amount of products. And how do you increase the amount of products while decreasing the amount of reactants? You move forward. Okay, so think of our fake reaction. If you need more products, you need to move this way. And when you move to the right, you're using up A and B. So these values will go down and C will go up until you get to K. Now, if Q is too large, there are too much products. So you need to decrease the amount of products and increase the amount of reactants. So you're going to move in the reverse. So if you move in the reverse, you're going to make more of A and B. So you're going to increase your reactants and decrease your products. So let's give this a shot here. So here we have a reaction between hydrogen gas and iodine gas. And we are making hydrogen iodide, and you have to balance it. Okay? So what is, it says that your equilibrium constant is 50.5. So we need to calculate Q. So remember, Q is, you set it up just the same way you would K, except you're going to put the little I there so we know it's the initial or the concentration at that time. Might not be the equilibrium concentration. And it's giving you the concentration. So it says that HI is 0.02, and you're going to square that, divided by H times I. And when you plug all that in, you're going to get 1.33 for Q. So that is obviously less. So Q is less than K. If Q is less than K, that means you don't have enough products and you need to move forward. So what happens when we're in equilibrium and everything is going smoothly, we're at equilibrium, but something comes along and disturbs our reaction. It stresses it, and it knocks it out of equilibrium. Well, the reaction is going to want to move in the direction that will take it back to equilibrium. So if a system at equilibrium is subject to a stress, then you will shift your reaction in order to reestablish equilibrium. And what are stresses? Well, by changing the pressure, or changing the concentration of either your reactants or your products, or changing the temperature. So let's see what happens when we do this. So how do these conditions change our equilibrium? Well, we will use Le Chatelier's principle to kind of predict which way the reaction is going to shift. And this diagram is from your book. I'm not going to go over it here, but I put it here so it's a reference so you could read it and understand what's going on there. But let's take pressure first. So let's take this stress first, pressure. Now, pressure will only affect gases. So if your reaction does not have gases in it, say it's all aqueous, changing the pressure is going to do nothing. So you have to make sure you have gases in your reaction. So you write your reaction and then you check, oh, do I have gases? Yes, I have gases present. Okay. And you also need a different amount of moles of gas on either side of the equation. So the check one is, do I have gases? Yes. Do I have different amount of moles? So here I have 1 mole and 3 moles on the reactant side. So I have 4 moles on the left, or the reactants, right? And I have 2 moles on the right, which are the products. So that is not equal. So that is good. You want to have different amounts of moles. So pressure will affect this. So pressure will have an effect. So how will it affect it? Well, when pressure is increased, or another way of saying that, volume is decreased, right? If your volume decreases of your container, your pressure increases, right? It will relieve this stress by moving towards the side with fewer moles. So look at my reaction here. If I increase the pressure, it will move towards the side that has fewer moles, which is the products. So my reaction will shift forward, okay? So if I increase the pressure or decrease the volume, they have the same effect here, right? Because by shrinking the volume, you're going to make the pressure in your container more. Then the forward reaction becomes favored, and it will move forward and produce more NH3 by using up. So the concentration of your reactants will go down, okay, until you reestablish equilibrium. Now, what is interesting is this will not change your equilibrium constant. Concentration, how does that affect it? So here we have this fake reaction here, and I'm saying you're increasing A. So I'm increasing the concentration of A. Your reaction will want to move to relieve the stress. I now have more A than I need. So I need to get it back down to where it should be. So how do I now take this higher concentration of A? I need to use it up. How do I use it up? Well, I proceed forward. I will proceed forward here. So you always want to move away from the high side. So by increasing the concentration of A, I made this too large. This is too large now. So it will move away from it, using it up, thus shrinking it down a little bit. But you will also make more of C and D. So by moving forward, you're going to end up increasing the concentrations of C and D. And B will decrease because it's going to get used up with your A. So your reaction will always move away from the higher side. So what would happen if D is decreased? So now I'm taking the concentration of D and I'm decreasing it. So now D is lower than it should be. So which side is high in this case? If D is low, that means this side is too high, right? So it will still move forward because it's moving away from the high side. Let's do the reverse. If I take D and I increase the concentration of D, now D is too high. So which way will it move? It will move in the reverse. Thus using up D and getting the concentration back down to where it needs to be. And interesting enough, by changing the concentrations, you still have no effect on K. Your equilibrium constant does not change. Changing the temperature. So changing the temperature, if you think about enthalpy kind of like a temperature and you treat it as either a reactant or a product, you can predict which way your reactant is going to shift. So there's two types of heat reactions, right? You could have endothermic. So if you have endothermic, you're going to put your heat as a reactant. And if you have exothermic, you're going to put your heat as a product. If I increase my temperature, I am now making my heat energy higher than it should be. So if this is high, which way is it going to shift? It will shift forward. So if I increase temperature for endothermic, it will shift forward, thus making more of C and D, using up A and B. Okay? Since I am making more of C and D, this is the only time that your equilibrium constant will change. So for an endothermic one, that you raise the temperature, you're going to produce more products, so K will increase because it's always products over reactants. For an exothermic, if I raise the temperature, I now increase my heat energy, and it's too high. So it will need to move away from the high side to the lower side. So it will shift to the reverse. So by increasing my temperature for exo, it will go in the reverse. So again, remember K is kind of related to your products over your reactants. So if I am moving in the reverse, I am making my reactants higher. So K will become smaller. Now, I'm going to write this big. Temperature is the only stress that will change your equilibrium constant K. So let's look at this graphically, because you're going to see some of these graphs and you have to really understand what's going on. So here we were at equilibrium, right here at the beginning. And then we added hydrogen. So when you add hydrogen, it jumps up to here. It was here at equilibrium. I added hydrogen, and it is now up here. Now remember, my here is my reaction here. I'll write it slightly bigger so you can see it. So I increased hydrogen, now making hydrogen too high. So what's going to happen? The reaction is going to proceed forward. It's going to move forward. Oops. When the reaction moves forward, I will now make more ammonium. So here was ammonium, and now my reaction is moving forward, so I'm making more of it until I reach a new equilibrium. What is happening to my hydrogen is decreasing down, and nitrogen also is decreasing because it's getting used up. Now hydrogen will end up being a little bit higher than it was because you added some to it. The nitrogen will end up being lower than it was because more of it was used up. Okay, but by moving forward, you're making more of your product and then reducing your nitrogen and a little bit of your hydrogen there. So let's look at a graphical representation of the pressure or volume change. So when gases are involved in equilibrium, a change in pressure or volume will affect the equilibrium. If I have a smaller volume, I have a higher pressure. And that will favor the side of the reaction with the fewer moles. So here we have this generic reaction of 2A going to B. So if I increase pressure, first of all, I have gases and I have different number of moles. It will move towards the smaller moles. So let's look at this. So here I am increasing pressure, and the smaller moles, in this case B, are green. Notice I have more green circles here, so I have more B here. Why do I have more B? Because the reaction's shifting forward. I'm making more B, and I'm using up A. So I have less A and more B. Now, if I decrease the pressure, it will move towards more moles. So that would be A, and notice I have more A here, more red balls than green balls. Temperature. So here we have an equilibrium reaction, and it's nice because it's different colors. Okay? It's endothermic, so the heat is a reactant. Okay? If the reaction is favoring the reactants, it's pink. If it's favoring the products, it's blue. If it's at equilibrium, it's a mixture of blue and pink, which makes purple. Okay? So if I raise the temperature, I'm going to increase my heat, which now makes it too high. So remember, you want to shift away from the high side. So if this is too high, I will shift forward. Making what color? It will become more blue. And let's look at our diagram. Let's see. What does this say? Heat. So if I am increasing the temperature, I will become more blue. If I remove heat, if temperature is decreasing, this now becomes, my heat becomes lower than it should be. So which side of the reaction is too high? If this is low, then this side's got to be high. So that means it's going to shift to the left, or the reverse reaction, and it should turn pink. And that's happening here. You see here it says cool, which means you're decreasing the temperature, which means your heat is decreasing. So we're going to go back to the Haber process again. I know it was on a few slides before, and we talked about it in a previous video. But this is very important in our society here. It allows you to take nitrogen from the air, react it with hydrogen, and make ammonia. This ammonia is really significant for agriculture, where we use it as fertilizers to grow plants that we end up eating. So it is very important to our livelihood that they can make ammonia. Okay, so if hydrogen is added to the system that we show here, it disturbs it, it stresses it, and now more nitrogen will be consumed, and the other two reactants will kind of form your NH3. So when they make this, they kind of establish their equilibrium. And this is the apparatus that they use to make ammonia. So this apparatus helps push the equilibrium to the right. We want to force our reaction to go to the right. Why would we want to do that? Because we want to make this. If we want to make this, we want to force it to move to the right. So there's a couple things you could do, right? You could increase the concentrations of your reactants. You could increase the pressure. But there's checks and balances, okay? You can't increase the pressure too much because it's expensive and it's very dangerous if it were to break and explode. So let's look at what they're doing here. So here, they're preheating the gases, and then they have a catalyst. We're going to talk about in a minute what the catalyst will do. And then it goes through all of this piping here, and you have a heat exchange. You're letting your hydrogen in, and you're letting it react, and then the NH3 will actually condense before the nitrogen and hydrogen, and then it'll drip out, and you could collect it. As it turns out, this Haber process is exothermic. So you would think that if you cooled it down, if it's exothermic, that means your heat is a product. If you cool it down, the reaction would move forward. And that actually is true, but there is a but in this case. The activation energy for this reaction is just so high. And if you cool it down too much, what happens to the kinetic energy of your particles? They decrease too much, and you can't get over the activation energy barrier. So you see how, yes, it's a very simple concept. Oh, I lowered the temperature, it'll move forward, I'll make more. But you have to remember, you still have to overcome your activation energy. And if you have a reaction that has a high activation energy, you still need the temperature to be significantly high so that you can get over that activation energy. So what do you do instead? You add a catalyst, because what does a catalyst do? A catalyst will lower your activation energy. And it will also allow you to do the reaction at a lower temperature, which will save money. High temperatures, you're burning fossil fuels, creating pollution, and it costs a lot of money. So, what does a catalyst do? It increases the rate of both the forward and the reverse reactions. So your equilibrium, you'll get to equilibrium faster. Why or how does it do this? Well, it lowers the activation energy. Now, the volume of the equilibrium constant does not change. The only time K will change is with temperature. Remember we said that? So look here. Here is our original, and the black line, and the green line has the catalyst. You have lowered your activation energy. So if you lower your activation energy, here is your rate plot. Notice it gets up to equilibrium faster. So here is another representation of it. So what happens is a catalyst will increase the rate of both the forward and the reverse reaction. So equilibrium is achieved faster. But the composition of your equilibrium is unaltered. It'll stay the same. So let's see if we could do a couple practice problems here and see how the equilibrium will shift. So here I have a reaction, and I'm going to increase the pressure. There's two things I need to check for. Do I have gases? And the answer to that is yes. The second thing is, are the number of moles different on both sides of the reaction? And the answer to that is yes. So pressure will have an effect. And how will it have an effect? I am increasing pressure. When I increase pressure, you're going to move towards smaller moles. Which, here I have 2 plus 1. Here I have 3 moles. Here I have 2 moles. So it will move forward. What happens if I increase the temperature for a reaction where delta H is greater than 0? If delta H is greater than 0, that means delta H is positive, which means it's endothermic. So why don't we write a reaction like this, okay? So it means it's on the reactant side. So if I increase temperature, I'm going to increase my heat, and we want to always move away from the high side. Now heat is high, so we're going to move forward, making more B, using up A. And what's going to happen to my K? If I make more B, my products are higher, so K will increase. If I add a catalyst, what will happen? Well, I will get to equilibrium faster. It will not shift in one direction or the other. I will just get to equilibrium faster, and my equilibrium K will remain constant. By the way, up here, K is constant too. Increase the amount of products. So if I'm going to increase the amount of products, let's say I have my A plus B, C, that means I'm going to increase the concentration of C. If I increase the amount of products, it will shift to the left. So I will make more A and B because it will shift in the reverse. And remember, K is still constant here. Because the amount of more A and B that I'm making, it kind of jives with the amount of C that is being used up. And they kind of, because you're dividing them when you take the ratio, it kind of cancels each other out, and K remains constant. So let's prove it. Let's consider a hypothetical reaction where K equals 1. Prove that adding oxygen will lead to a shift towards the product. So my K for this reaction is equal to 1. So I'm going to assume that at equilibrium, the concentrations of everything is 1. That just makes it simple, right? So the concentration of SO3 will equal 1, SO2 will equal 1, and the concentration of oxygen will equal 1 at equilibrium. I need to calculate Q. So it says here, by adding more oxygen, I am not at equilibrium anymore. So I'm going to, well, remember Q is the same relationship, but you're using values that are not at equilibrium. And according to our problem, everything is remaining the same except oxygen. So I'm going to say that my concentration of oxygen, I'm going to double it. It's going to be 2. So let's plug it in. The rest are going to remain 1. So let's plug everything in. So I have 1 squared divided by 1 squared times 2, and that just equals 0.5. Okay? So now Q is less than K. When Q is less than K, I do not have enough products. So how do I get more products? I need to shift forward to make more products so that Q will increase until it becomes equal to now let's look at it this way. If I increase my concentration of oxygen, This side is high. I always move away from the high side. I'm going to move forward. So you see, this using Q and K proves Le Chatelier's principle. So I am not going to read this summary. I put it here for your reference. You should go back and read it, take notes, highlight what you think is important. But this talks about all of the stresses, how they affect which way the reaction is going to move, and how they affect K. This is the end of part 3.